So good afternoon, all of you. Today we are going to see about the principles of radiation detection. As of we know all that radiations we are using for so many applications, but what do you think? We have to need we should need some device or any material which gives you idea about this presence of radiation. So for that purpose we are going to see today what is radiation, types of radiation, how they interact with the medium, and the detectors which detect this presence of radiation. Hmm. So first of all, we will see about what is radiation. So radiation is the emission or transmission of energy in the form of waves or particles through space or through a material medium or from the nucleus of an atom. So it is the emission or transmission of energy in the form of waves or particles from one medium to another medium. So, and these includes electromagnetic radiation such as red waves, microwaves, visible light, ultraviolet, X-rays, and gamma rays. So, radiation is a form of energy like heat or light emitted through space and matter, and which cannot be detected by any of our five senses. So, there is a need of such detectors which tells you about the presence of radiation, how much its intensity, its energy, and which type of radiation is present in that area. So for this we require detectors. So first we'll see types of radiation. There are two types of radiations present in electromagnetic spectrum. First one is non-ionizing radiation and second is ionizing radiation. Non-ionizing radiation means the radiation that does not have sufficient energy to dislodge or knock out an electron from the orbits of the atom. Means these radiations like microwaves, ultraviolet light, lasers, radio waves, and infrared, they don't have a sufficient energy to eject an electron from that medium. Means it doesn't have a sufficient energy to ionize that medium when they pass through that medium. And second is ionizing radiation, means radiation that has sufficient energy to ionize the medium when they pass through that material, like alpha particles, neutrons, gamma rays, and X-rays. These have a highly energetic radiations. When they pass through that medium, they start ionizing that medium, like the ejection of electron and positive ions are created in that medium. So first we will see the alpha particles, means alpha particle, beta particles, gamma rays, X-rays. These are the ionizing radiations, and we cannot sense these radiations, so we need a detector. For that purpose we have to study their properties in the medium, how they interact with that medium, and what are the things we can study with the help of this detector. So alpha particles, they are a monoenergetic in nature and loses energy in a more or less continuous slowing down process as it travels through the matter. So when these alpha particles pass through any medium, they continuously interacting that material and producing positive and negative ions along their paths, and slowly their energy goes on decreasing, and at last they lose their all energy, and that how much distance traveled by that alpha particle is the range of that alpha particle. The distance it travels depend only upon its initial energy of that alpha particle and its average energy loss rate in the medium. Its average energy loss per unit time in that medium, which gives the range of that alpha particle, and the range of our alpha particle emitted in tissue is on the order of micrometers in range. Beta particles, they are in continuous energies. We are getting a continuous energy spectrum for these beta particles, and beta particles range vary from one electron to another electron, even for betas of the same energy in the same material. If we consider a beta particle having an energy of 1 kilo electron volt and the medium is water, but every beta particle different interact differently in that medium because of the elastic and inelastic, so many collisions occur with that medium, so they deposit different energy in that same material. The beta range is often given as the maximum distance the most energetic beta particle can travel in that medium, and the The range of beta particles emitted in tissue is on the order of millimeters. So types of interaction. There are two types of interactions. One may happen ionization and another is excitation. In ionization, what happens when any incident radiation interacts with any of the material, they transfer their energy to that electrons, atomic electrons, and the electron is ejected. So positive and negative ions will be formed. So that is the ionization process. In excitation, what happens when incident radiation interacts with that medium, they do not have sufficient energy, only they transfer the energy to that electron, and that electron may go from ground state to excited state, but it will not ejected from that orbit. So that process is called excitation. And main fundamental phenomena important for radiation detect is ionization. There should be ionization should be happen to detect the presence of radiations, and media, whatever means the solid, liquid or gases, we can use for the detection of these ionizing radiations. So when these radiations interact with any medium, there are 5 types of interactions may happen, like coherent scattering, we call it as a relay scattering also. In this, what happens, photon deflected with very little energy loss, means when incident photon interacts with that medium, then it will transfer some amount of energy and deflected with very little energy loss, and it sets only the vibration of that oscillation of that electron, but it will not able to eject that electron from that medium. So that is a coherent scattering, and it happens with low photon energies below 50 kilo electron volt. Next is a photoelectric effect. In this, what happens, when incident radiation interacts with that material or that medium, that photon transfers its all energy to that electron, and that electron is ejected from that medium, and whatever the vacancy is created in that orbit, that is filled by another outer orbit electron, and whatever the energy difference is there between these two orbits, that may be emitted in the form of X-rays or heat. It depends on the energy of the energy difference between these two orbits. Means here the frequency of that incident photon matches with the binding energy of that K shell or L shell electron, and they are ejected from that medium. Next comes the Compton scattering. For Compton scattering, the energy of the photon should be more than the photoelectric effect. So in this, what happens, highly energetic incident radiation interacts with the atomic electrons, like a free electron which is in the outer orbit of that medium. So this Compton scattering depends on the electron density of the material. When incident radiation interacts with material, it ejects free electron from the orbit, and also that excess energy that is scattered in the form of scattered photon, and this scattered photon continues with lower energy. Next comes the pair production. So in this, the threshold energy for that photon is 1.022 mega electron volt. So when this highly energetic incident radiation interacts with medium, the positive and electron pair is created, and we call it as a pair production. So these are the types of radiation and type of interaction we have seen when this radiation interacts with or transfer their energy to the medium. So what here the key element is what? Ionization, which is means ionization is the key to its risk. Like ionization causes chemical reactions in cell interfere with metabolism, reactions in DNA interfere with genetics. These are the ionization is the key to risk. Also, ionization is the key to its use. Means with the help of this ionization phenomena, we can use in the so many detectors like medical or material analysis or research. In that case, we can use like a medical. So ionization is helpful to kill the cancer cells. Material analysis to which type of material is present. In that case, we can use these radiations. In research, we can use this radiation. So the ionization is the key to its use also, and ionization is the key to its detection. So because of this ionization radiation property, we are getting some variation in the parameters of that medium, so we can detect the presence of any ionizing radiation directly or indirectly, depends on the equipment or the design of that detector. So what happens when ionizing radiation interacts with the medium, they produce ionization. Ionization electric charge is produced, and that electric charge is with the help of electronic circuit we can measure. Why do we measure radiation? Because in safety, because we have to measure or detect this radiation, because radiations, if we use in some special limits or specific limits, within that those limits, then they are giving benefits, but if it crosses that limit, then they are harmful. So we have to check the presence of radiation and what level radiation level is present to protect the public and the environment. So for that purpose, in case of safety, we have to check is the radiation level is above the threshold value or below. Dose rate in medicine and reactors, in that case we can use this detectors. So in medicine we are using X-ray, SPECT, PET, CT scan, and radiation therapy for cancer. In that case we have to monitor the doses we are delivering to the patient. And for that we require detectors. In industry we are using for sterilization and for XRD analysis of that material. In that case we are using radiation, so we have to make sure that whatever the radiations we are using, they are safe or no. And in research also we are using these radiations, because means we are getting benefits from the radiation, but if it exceeds that safe level, they are harmful to the human being and the environment. So we have to measure these radiations, and for that purpose we need a detector. So what properties of radiation we can measure with the help of these radiation detectors are: presence of radiation. So is there any present above a threshold or no? Means it is within low level radiation or higher level or high risk radiation levels are present, that we have to survey continuously to check the radiation area. Amount of radiation is its fluence, dose, its flux, its number of interactions per unit square, per centimeter square area, number of photons per centimeter square area per second, flux, is radiation damage. So which type of radiations are present, like alpha particle, beta particle, X-rays, neutrons, like that. And energy, time of interaction, and position, these are also useful factors in imaging. So many other quantities could be of interest, like energy spectrum, like energy distribution of that radiation. So in basic radiation detector system, some major components are present, like detector means one type of material which tells you about the presence of radiation. Then whatever the signal is produced with the help of ionization, that signal or pulse or current, that should be amplified and conditioned and then transferred to the analog to digital converter and then stored to the disk. Such type of detector system is there in this basic radiation detector system. So we want to know about the radiation, its energy, position where it is interacting, its location, and how many, means how much is the intensity, and interaction rate that we can measure. So important properties of radiation detectors, it depends on the application. If we want a higher energy resolution, such type of detectors we have to choose. If we want a spatial resolution, then we have to choose such detectors which give you a higher spatial resolution. In some cases we require a higher sensitivity, but we can compromise between energy resolution and spatial resolution. So in that case we should choose that higher sensitivity detectors and the counting speed. So now we will see principle of radiation detector. So in this, what happens, ionizing radiation is most commonly detected by the charge created when radiation interacts with the detector material. So ionization is the main phenomena that makes radiation detection and measurement possible. So when charged particles like protons or electrons are incident on the detector material, they continuously interact with these atomic electrons of the detector material and produce a electron ion pair. In case of semiconducting materials, it produces electron hole pairs along their tracks, and this initial energy produced by radiation is most important information and further processed by a proper signal processing electronic after collection. So for this is the direct direct interaction of protons or electrons. They directly interact with that material and produce ion pairs, and that ion pairs are collected and processed further to getting the information of that radiation. When neutral radiations like photons, like gamma rays or neutrons or X-rays, they are measured by a neutral particle. These neutral particles interact with the detector material, and then the product secondary charged particles like electrons, protons or alpha particles are created, and these charged particles are responsible to deposit their energy into that detector material, and this means we call it as an indirect effect, and we can measure the whatever the charge produced in that material. There are so many types of radiation detectors are present. One is the gas field detector, scintillation detector, solid state detectors, and photographic emulsion. So in this gas field detectors, we can study three types of radiation detectors like ionization chamber, proportional chamber or proportional counter, and Geiger-Müller counter. So we are going to see about this gas field detectors in detail. So gas field detectors consist of a volume of gas between two electrodes. In scintillation detector, what happens? The interaction of ionizing radiation produces UV or visible light. And in semiconductor detectors, like a pure crystals of silicon or germanium or other materials which are trace amounts of impurity atoms have been added so that they act as a diodes, and we can get the information from this different types of radiation detectors. So based on the type of information we have produced, there are some classification of these detectors like counters. So detectors such as GM counter detectors that indicate the number of interactions occurring in the detector are called counters. Means this gives the information about number of interaction happened in that detector. So spectrometers, which gives you the information about the energy distribution of that incident radiation when it interacts with that detector material. And dosimeters means these detectors will give you the net amount of energy deposited in the detector by multiple interactions in that material. So now we are going to see about gas field detectors in detail. So it is basically a metal chamber filled with gas and containing a positively biased anode wire. A photon passing through the gas produces free electrons and positive ions, and the electrons are attracted to the anode wire and collected to produce an electric pulse. This is the basic principle of gas field detector. So gas field detectors, the passage of a charged particle through a gas results in the transfer of energy from the particle to electron, and that are part of the normal atomic structure of gas. If the charged particle passes close enough to a given atom, the energy transfer may be sufficient to result in an excitation or ionization. So in the excitation process, an electron is elevated from its original state to less tightly bound state, means excited state, and energy levels in the typical gas atoms are only spaced a few electron volts, so that the energy needed for excitation is a small fraction of the kinetic energy of that typical radiation quanta. So in case of excited state, there is a specific lifetime before the atom decays back to its original ground energy state. So typical mean lifetime for excited atomic states in gases are normally only a few nanoseconds. Means when the incident radiation passes through or close to that atomic nucleus, it transfer its energy to that electron, and electrons get ejected from ground state to excited state, and for a such for specific period of time it again decays back to the ground state and it emits a photon.
Sir.
So when radiation passes very close to the any medium or atomic nucleus, it has a sufficient energy to eject, transfer its all energy to that medium and totally remove an electron from that medium. This is the process of ionization and results in the creation of an ion pair. So because the ionized atom is electron deficient, it carries a net positive electric charge and is called a positive ion. One is the electron and next is the positive ion. The other member of the ion pair is the electron that is no longer bound to a specific atom and is known as a free electron, and it is responsible for the getting a electron motion of electrons means current in the as a output. So the ionization potential or the minimum energy required to remove an electron is about 10 electron volt for the gases typically used in radiation detectors, and the W value, which is defined as the average energy lost by the incident particle per ion pair formed. So due to the competing mechanism of the energy loss, that is excitation, W value is always greater than the ionization energy. So W value gives you about the average energy lost by the incident radiation to create a one ion pair. So approximately 30 electron volt of energy lost by the incident charge particle is needed on average to create a one ion pair. So the remainder of the energy is expended in various excitation processes, or it may be in the form of heat. So here are some ionization potential and W values for different gases like argon, helium, hydrogen, nitrogen gases. First, ionization potential is in the range of electron volt, 15.7 electron volt for argon gas, and W value means to how much energy or the potential is required to create a one electron hole pair is for fast electrons is 26.4 and alpha particles is 26.3. So many gases are given here with their potential, ionization potential and W value. So different types of collisions happen between these free electrons and ions and neutral gas molecules as shown in this figure, like a charge transfer, electron attachment and recombination. After interacting with the detector material, ionization occurred, and after occurrence of this ionization, there are so many collisions may happen in the electron, positive ion or the neutral gas molecule, like so these are the processes like a charge transfer which occurs when a positive ion encounters a neutral molecule. In this case, an electron is transferred from the neutral molecule to that ion, and when a free electron meets a gas molecule that attaches electrons easily, a negative ion is formed, and oxygen is a good example of electronegativity. So in this what happens, free electrons diffusing in air are rapidly converted to negative ions. In contrast, nitrogen, hydrogen and noble gases have low electron attachment coefficient and make electron continuously migrate. So nitrogen, hydrogen and noble gases are mostly used in the detectors because they are responsible to migrate that electrons continuously. Oxygen is a poor used in the detector because it has the capacity to attach this free electron to the neutral molecule and convert it into negative ions. So ionization chamber must have a sufficient potential difference across the anode and cathode to collect all the free electrons produced. So when ionization occurs, then whatever the two electrons are present, the sufficient potential difference should be applied between these two electrodes to collect whatever the ion pairs are collected. If the potential difference is insufficient, then recombination occurs and information is lost. And if the potential difference is too great, additional free electrons can be produced by secondary interaction within the chamber, and it will give the excess or the information which is not a true one. So we have to optimize between this potential difference depending on the application. So electrons freed by the primary interaction of the incident radiation may have sufficient energy to produce secondary free electrons, and that's okay because the energy transfer originated from the primary interaction. So these are the regions of gas filled chamber. So here we are going to see current versus applied voltage graph. In there are 6 regions are there. six regions are there of the gas filled chamber. First is the recombination region, second is the ionization chamber region, third is the proportional region, then comes limited proportionality region and Geiger-Müller region and continuous discharge. So these are the regions we are getting when on what voltage we are applied to that detector to that electrode. So first is the recombination region. So at very low voltages the ion pairs recombine to form neutral atom before reaching electrode. So what happens when incident radiation interacts with that metal, it produces ion pairs, positive and negative electron. And if the sufficient voltage is not applied between these two electrodes, while moving that ion pairs, they recombine and the information may be lost. So recombination decreases as applied voltage increases. Then comes ionization region. So in this region, all ion pairs, whatever they are created, they all are corrected because the sufficient potential difference is applied in this ionization region. So in a limited voltage range, the number of ion pairs produced and collected remain constant, and this region independent of voltage but dependent on energy deposited in the detector volume. So individual events cannot be detected, only the total current passing through the chamber is measured. Means we cannot detect in each and every interaction, but at last we can collect the current created by the different interactions. And because specific ionization differs for alpha, beta and gamma radiation, the amount of current produced by these radiation differs in this region. So depending on the initial energy or the interaction mechanism of that individual particles or radiations, we are getting a different amount of current produced. So we can easily identify or we can easily measure the how much energy deposited by that individual radiation in that material with the help of this ionization region, and the voltage in this range is in the order of 50 to 300 volt. So in this range we get the ionization region. So another important phenomena involved in this detection mechanism is the gas amplification. When the applied voltage is further increased beyond the ionization region, the electrons and positive ions gain such high velocities and energies during their acceleration toward the electron that they cause secondary ionization. So when we increase the voltage beyond this ionization region, that potential, whatever the energy is applied, a potential difference applied between the electrodes, these ion pairs get excess energy from this potential difference and they may get accelerated, and during acceleration while reaching towards electrode they may ionize further neutral gas molecules. So we'll get a increase in the measured current at the output. So this process is referred as the gas amplification, and this factor can be high as 10⁶ per individual primary event depending on the design of the gas detector and the applied voltage. So in this figure we can see about how this multiplication process occurs. For one electron we are getting 2 electrons, then 4 again get multiplies, and so in another image we are getting the electric field strength on x-axis and electric field on the y-axis. So here how we are getting the response. So initially we are getting a 2 means ionization region, and when the potential difference increase up beyond the threshold value, we will get a sudden increase in the output, means gas multiplication occurred. So next comes the proportional region, and whatever the detectors we are using in this proportional region, we call it as a counters. So in this region of applied voltage, the counter is above the threshold for gas multiplication, and the total current measured is equal to the number of ionization caused by the primary radiation multiplied by the gas amplification factor, because for every gas there is a different multiplication factor, gas amplification factor, and whatever the information we are getting, to that we should multiply the gas amplification factor, and total current we will get at output. So the multiplication is linear. The collected charge is proportional to the number of charge pairs created by the incident radiation. So constant of proportionality amplification is increased with increasing the voltage, and the pulse is dependent on the radiation type, but importantly it is dependent on the incident radiation energy. So in this, whatever the information we are getting is it is dependent on the type of radiation and how its initial energy of that incident radiation. So with the help of these proportional counters, one can identify the type of radiation and its energy. So therefore, at fixed voltage, measured pulse amplified or height proportional to incident particle energy, and in this region the current increases with the applied voltage in the proportion to the initial number of amperes produced by the incident radiation. So therefore, as in the case of region of saturation, the current amplification is relatively proportional to the type of radiation, like example alpha particle, beta particle or gamma radiation. So in this region we can identify which type of radiation is present and its interaction or how much energy deposited by that radiation. If we further increase the voltage to these gas field detectors, we will get the limited proportionality region. So the increase in applied voltage results in non-linear effects. Beyond this proportional counter, if we increase the applied voltage, we will get a non-linear effects. In some amount of energy amperes are created, but they are giving but it is non-linear to that initial number of charge produced. So at last we are getting some different outputs which is non-linear to the primary ion pairs. So we cannot use any detector in such region. So the free electrons are quickly collected due to high mobility, while positive ions are moving slowly, which takes a long time. And during the collection of the electrons, an almost motionless cloud of positive ions are created, which is slow to disperse, and if the positive ion concentration is high, the electric field is get distorted because of this cloud of positive ions and leads to distortion, gas multiplication, and non-linearities are observed, and amplification is not constant as space charge alters shape of electric field, and so that's why we cannot use this region for the radiation detector purpose. Next is the Geiger-Müller region. If we further increase voltage to these detectors, they overcome that applied voltage which is responsible for that formation of cloud. It overcomes, and they fastly attracted to the anode and cathode, and will get a uniform electric field in this region, and the applied voltage is made sufficiently very high, one ionization event sufficient to trigger a discharge. And so in this detector we cannot get any difference between the pulse height, because a single trigger can get you the give you the high discharge or high production of ion pairs because of the applied voltage which is very high, and number of multiplication occurs, and at last for a small input we will get a higher output, and that pulse height we are getting is not related to the incident energy deposited by that radiation. So the amplification factor may be as high, hence this detector very sensitive to detect the low level radiations, but it cannot give you the information about which type of radiation is present and how much is the energy of that incident radiation, but we can detect which is the presence of radiation. So in low level radiation fields we are using this GM counter, and then comes the region of continuous discharge which occurs, sparking takes place, not useful for the detection. If we further increase the applied voltage to this region above Geiger-Müller region, the continuous discharge region will happen, and a single ionizing event produces a series of repetitive discharges leading to what is called as spontaneous discharge, and gas may be ionized in the absence of radiation at this high voltage, and operation of detector in this region may cause damage to the detector. So this region is also not useful for the detection purpose. So these are the 7 regions we have studied about gas field detectors, and out of these regions we can use only ionization region, proportional region, and the Geiger-Müller region for the detection purposes. Thank you.